Okay, welcome back. It's 9.2. Finally, we're going to talk about series. So we're getting closer to this idea of being able to approximate pretty much any function with a polynomial so long as the function has a bunch of derivatives. And the series are the connection between the sequences and these polynomials, kind of, right? It's a kind of a long story, and I wish I could give it to you in one foul swoop, but not really. Anyways, let's take a look at what we got. So first off, the infinite series. What the heck is this thing? It's just a sum of a bunch of terms of a sequence, basically. So it's a sub 1 plus a sub 2 plus dot 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 plus some general a sub n plus dot 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 forever and ever and ever, right? This formula here is the nth term formula for the terms, for the term, nth term of the series. Nth term formula for the nth term of the series. Okay, so it's a little weird because each one of the things like this guy right here will have kind of a sequence formula, right? But you're using the sequence to generate the terms of the series, and then the sequence that we're actually concerned with is the sequence of partial sums formed from that. Okay, so we'll be worried about the sequence of partial sums and whether or not that thing converges. So for example, from before, we may have had something like a sub 1 is, I don't know, 1, a sub 2 is 3, a sub 3 is 5, etc. And then a sub n would be 2n minus 1. Whoops. Now we're adding these things up. So our first partial sum will be 1. Our second partial sum will be 1 plus 3. Our third partial sum, third partial sum will be 1 plus 3 plus 5. Okay. So each one of these has its own, sequence value. This is 1, this is 4, this is 9. But the terms of the sum are given by kind of the sequence formula a sub n over here. So on and on until s sub n, which would equal the sum from I equals 1 to n of 2i minus 1. Just like before, we'll be worried about finding the limits of these nth term formulas. It's going to be a little more difficult now because when we're dealing with the limit, we're taking the limit of a sum. So back here, we would just have a nice little formula for that, which would be 2n minus 1, and we could easily see that that would go to infinity. But over here, it's not clear, right? So what the heck is this thing, right? The limit of this sum of this sequence. So we'll spend a lot of time looking for formulas for this thing right here, and then taking the limit of that, and then we'll kind of go up a level from there and classify different kinds of sums as certain types, and then based off of their type, we'll say they're convergent or divergent. In other words, the limit of the sequence of partial sums exists or it does not exist. Okay, okay, so let's look at number 5. We have the sum from n equals 1 to infinity of 3 all over 2 to the n minus 1. They want us to find the first 5 partial sum terms. So find S1, S2, S3, S4, S5. So the terms of the series itself are a sequence. right? But we're not interested in that particular sequence. We want the sequence based off the sum of the terms of that sequence. So S sub 1, if I plug 1 in, I'll get 3 all over 2 to the 0, which is 1. S sub 2 will be S sub 1 plus S sub 2, which is 3 all over 2 to the 1. S sub 3 then, 3 over 1 plus 3 over 2 plus 3 all over 2 to the 2, which is 4. S4, 3 over 1 plus 3 over 2 plus 3 over 4 plus 3 all over 8. And then S5, 3 plus 3 over 2 plus 3 over 4 plus 3 over 8 plus 3 over 16. And again, we're going to be concerned with the limit of this sequence, in this case, the limit of partial sums as n goes to infinity. And so in this case, you could kind of try to get a formula for each partial sum. So I'm just going through here kind of trying to identify maybe a pattern of some sort. So 24 plus 6, 30, then 42, then 45 plus 48. It's 93 all over 16. Okay, we're trying to find the limit of what this thing is as n goes to infinity. And off the top of my head, I don't see any sort of sequence popping out at me. Any sort of formula that would give me this thing, this S sub n thing. So is there an nth term formula that would allow me to place it in here and then take the limit? Okay. So that's a question that's put forward to you. Sometimes you'll be able to find that formula, this S sub n formula, and the first place you would see that would be the telescoping series. Okay. So with telescoping series, you can actually do that. And to pull it off, you're going to do a partial fraction decomposition. Okay, to find this nth term S sub n formula. So in particular, we look at 27. This is the same thing as the limit as n goes to infinity of the sum from I equals 1 to n. Okay, the only difference between this and this is I'm letting this top part go to, I'm sort of putting it into the limit, the fact that it's going to infinity, of 4 all over I times I plus 2. So I want to find a formula for this thing here. And I'm claiming I could do that with a partial fraction decomposition. So in particular, let's just remove this part of it and decompose it. Okay, then we could rewrite this thing in parentheses, which is our S of n. We're after this a formula for S of n. So we could rewrite this using our partial fraction decomposition. So we'll have 2 over I minus 2 over I plus 2. So to get this formula, I do what's called telescoping. So I expand it and then let it collapse. And what I'm left with will be a formula for this object, this S sub n term. So I'll just look at the first couple terms. So I'll have 2 over 1 minus 2 all over. If I put 1 in for I get 3. Plus 2 over 2 minus 2 over 4 plus 2 over 3 minus 2 over 5. Maybe one more term just so we can see what's going on. 2 over 4 minus 2 over 6, sorry. This is I equals 1, 2, 3, 4. And then plus dot, 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 plus. Then I'm just going to put the last 3 terms in. So first off, I equals n minus 2. Oops, this should still be 2. I'm using this formula. And I'm plugging in I equals n minus 2. So n minus 2 plus 2 is just n. Then I equals n minus 1. And then finally, I is n. And what you should have is a collapse, okay? A lot of cancellations, and you kind of have to do it intuitively. It's not, something you want to write home about to your dad who's a professor at Harvard. He's not going to be impressed, right? So you just kind of feel it out. So 2/3, this guy is going to cancel with this guy. This 2/4 will cancel with this guy. This second term is going to cancel with the first term in the next element. This second term will cancel with the first term and the element after that. And then here, there are basically 2 things before this guy. And then in the second thing here, there's 1 term before it and then the second term before that. And here, the second term will cancel with the first term here based off of this pattern here. So I'm just, if I have this guy here, it's going to cancel with the first guy jumping like that. So if I jump over this term here, the second guy here cancels with this first time here. And then the second guy here will cancel with this guy here. And then clearly the second term here will cancel with this guy here. And then that's it. The second term here won't have anything to cancel. The second term here won't have anything to cancel there. So then you just kind of figure out what's left. So what is left? We have a 2, 1, 2 over 2 is 1, so 2 plus 1, and then minus 2 over n plus 1, minus 2 over n plus 2. And that's going to be our formula for S of n, this magic formula such that in the last problem, I couldn't really figure out what the heck it was, right? So in the last problem, I couldn't figure out this S sub n formula for the terms of the sequence of partial sums. I was like, what? But in this kind of problem, you could do that. right? And it's sitting right here. So at the end, you need to put it back into this limit and actually figure out what this equals. Okay? So this is just scratch work, basically. So I'm putting this formula into here, and I get the limit as n goes to infinity of 2 plus 1 minus 2 over n plus 1 minus 2 over n plus 2. Okay, then this will go to 0, this will go to 0, and you're just left with 2 plus 1, which is 3. Okay, so in that case, we'll say this series converges. And you could think of this as a sum. If you were to think of this as adding up a bunch of things together, this plus this, etc., you could think of it as equaling 3. Okay. Another situation where we can obtain an explicit S of n formula will be the geometric series. Rather than handling series by series cases here, we're going to kind of group all the geometric series into a class and determine if they're convergent or divergent based off of the factors in the series. So our geometric series, the sum n equals 0 to infinity of AR to the n. So what is that? It would be A plus AR to the first plus AR to the second, etc. Okay, so in general, we'll say the sum from n equals 0 to infinity of AR to the n will converge to A over 1 minus R if the absolute value of R is less than 1 and greater than 0. You wouldn't be able to work with this expression if R was equal to 0. It would just be 0 plus 0 plus 0. So they also make the restriction that absolute value of R is greater than 0. And then it's divergent if the absolute value of R is greater than or equal to 1. Okay. So in practice, these problems are pretty simple. Sum n equals 0 to infinity of 7, 6 to the n. So you identify the A value, the R value, and then determine its sum or say it's divergent depending on the R value. So here the A value is 1 and the R value is 7, 6. Okay, so in this case 7, 6 is greater than or equal to 1. So it's divergent. It does not have a sum. So I don't want to say it's equal to divergent. We just say this sum is divergent. Let's look at 15. The sum from n equals 0 to infinity of 5, 6 to the n. Okay. In this case, again, A is 1, R is 5, 6. Okay. So this one works, right? The absolute value of R is 5, 6. So if we took its absolute value, you'd get 5, 6. And that's definitely less than 1, but greater than 0. So it's convergent, and it converges to A over 1 minus R. So this will equal 1 all over 1 minus 5, 6, which is 1 all over 1, 6, which is 6. Oh, sorry, 6, 6. Yeah, that's right. Did I get it wrong in my notes? Yeah. Clever things you could do with this, then, is figure out rational or fractions for repeating decimals. Okay? So problems like 37, 0.81 repeating. Okay? Okay, so you can think of this decimal as a sum of finite decimals. So it's a sum of 0.81 plus 0.0081 plus 0.000081, okay, on and on. The R value is the ratio between two consecutive terms. Okay, so R will be the ratio between 0.0081 and 0.81. Okay, so you can move the decimals if you want. So I'm getting, sorry. 81 all over 10 hundred thousandths, 10,000, all over 81 all over 10 hundredths, which is multiplying by reciprocals, 100 all over 10,000. Then you can remove zeros, and it's just 1 all over 100. Oops, I removed too many zeros there. It's 2 zeros. The A value will be the first value you see, so that's the 0.81, because this is A. If you remember the original definition, this is A plus AR squared plus dot, dot, dot. Okay, so I can rewrite this repeating decimal as a sum from n equals 0 to infinity of A, which is 0.81, times R, which is 1 over 100, to the n. In that case, we can also get the rational form of this decimal, repeating decimal. In other words, the fraction form. It's you know, A, which is 0.81, all over 1 minus R. So this will be 81 all over 100, all over 99 over 100. Multiplying by reciprocals, it's 81 all over 99. 81 99ths. Okay. The derivation for this particular formula is vaguely interesting. It's clever, if nothing else. I just wanted to introduce you to it. It's in the book, The Proof of Convergence. So in particular, just considering the values where the absolute value of R is not equal to 0 and not equal to 1, I believe is where we want to go with that. You can take a look at the partial sum. So S sub n will be A plus AR plus AR squared plus dot 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 plus, if this is our 0th term, the let's see how I want to think of this. The last term will be the n minus first term. Okay, so the last term will be AR to the n minus 1. And then we're going to sort of subtract away a multiple of that. So if I multiply this first guy by R, you'll end up with just the same thing shifted over one place, so to speak. So you multiply everything here by R, you'll get AR plus AR squared plus dot 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 plus AR to the n minus 1 plus AR to the n. And then you add it up, you get S sub n minus R S sub n equals A minus AR to the n. Factor out the A. over here factor out the S sub n. The formula for the nth partial sum will be A all over 1 minus r times this factor 1 minus r to the n. So the limit as n goes to infinity of this thing is solely dependent on the behavior of this one term here. It's the only term that depends on n. And note, the limit of r to the n will equal 0 when the absolute value of r is less than 1 but greater than 0. In other words, it's convergent in this case. And then the limit as n goes to infinity of r to the n will be plus or minus infinity if the absolute value of r is greater than 1. Okay. I guess I'm thinking, is it ever equal to negative infinity? And if r is positive, it'll definitely go to positive infinity. If r is negative, you're going to have terms like negative 3 squared, negative 3 cubed, negative 3 to the 4th. So it's going to have that kind of oscillating behavior. In other words, it's either going to be positive infinity or it won't exist at all. In either case, we'll say it's divergent. Okay, so this, if you look back in your notes anyways, this case will be divergent when r n goes to some sort of infinity or it doesn't exist. If this thing equals 0, that's the case when the r value is less than 1. Okay. Okay, and the cases where r is 1 and r is negative 1, you can look at those on your own, or you can ask me in class, after class, and I'll explain it to you. But that's the idea. The cleverness that every calculus student should see is this first part, though, taking the sum and then subtracting away the sum times this factor of r will just produce a nice formula for S sub n. And then it's this formula we're taking the limit of, and we're classifying all of these geometric series dependent on the r value. Okay? So the job is done as soon as you're given one of these sums. You could just look at it and you know automatically whether it's convergent. That's when r is like 1/2 or negative 3/5 or something. And then you'll also automatically know when it's divergent. That's when r is 5 or r is negative 5. Okay, a couple more things for our journey. Three more things. The nth term test for divergence, which is extremely important. Literally, the first thing you want to do when you get a series in the future is this test. So it says, basically, if the series A sub n converges, then the limit of the terms of the series as n goes to infinity is equal to 0. On the other hand, if the limit of the terms of the series as n goes to infinity is not 0, then the series is divergent. Okay, please note that the converse of the statement is not true. Right? You cannot say the limit of a sub n equaling 0 tells me something. And you'll wish it would, but it doesn't. Just this by itself doesn't tell us anything. Other little factoids. Basically, if you have a series converging, you can multiply it by a constant and it will still converge, and vice versa. The other factoid, you can chop off a huge part of a convergent series, it will still converge. You could chop off a huge part of a divergent series and it will still diverge. So if the sum from n equals 1 to infinity of a sub n converges, then the sum from n equals big M to infinity of a sub n will also converge. And then likewise, if the sum from n equals 1 to infinity of a sub n diverges, and you multiply it by a constant, it will still diverge. Okay. So these are helpful hints for your journey. So it's a lot like when you're dealing with integrals. If you want to integrate 3 all over x dx, factor out the 3, right? And then what you have left over with is this identifiable integral that we have a formula for. So now in the terms of series, if you have the sum from n equals 0 to infinity of, let's say, 3 times 2/3 to the n, you know that this is just 3 times n equals 0 to infinity of the convergent geometric series with a equals 1 and r equals 2/3. So you can always just factor that thing out and you get 1 all over 1 minus 2/3, which will be 3 all over 3/3 minus 2/3 is 1/3, which is 9. Okay. Let's look at some of the ones in the book. Number 9, the sum of n all over n plus 1 from n equals 1 to infinity. If you take the limit of n over n plus 1, what do you get? Well, you get 1. This is not equal to 0. That tells me it's divergent. Let's look at 53. The sum from n equals 1 to infinity of tan inverse of n. Again, if you take the limit as n goes to infinity of n, tan inverse of n, you're going to get pi over 2, which is not equal to 0, which means it's divergent. Okay. An example like this one. So we can figure out the limit of 1 over n as n goes to infinity. That's equal to 0. This tells us nothing. It's only when it doesn't equal 0 that it gives us information. So in this case, this is actually a well-known series called the Harmonic Series, which is divergent. And of course, we can compare and contrast that with a telescoping series. looking at the one we did earlier. The sum of 4 all over I times I plus 2 from I equals 1 to infinity. If I do the limit of this expression, I would have gotten 0. And that tells me nothing. It turns out that this thing is convergent, but I couldn't make that conclusion from this fact because there are series that are divergent such that the limit of the terms of those series is also equal to 0. Okay, one last example, the ball bouncing problem. Okay, we're trying to find out how far the ball travels after being dropped from 16 feet. Okay, so first draw a picture of what's going on. The ball first drops 16 feet, and then each time it bounces, it's rebounding 0.81 of the original amount fall that it fell. So it's going to go back up 16 times 0.81, and it's going to fall back down by that same amount. Then it's going to rebound 16 times 0.81, and I multiply that again by 0.81, I get 0.81 squared, and then it falls back down. Okay. So the sum will be 16 plus 2 of these guys, so 16 times 2 times 0.81 plus 2 of these guys, so plus 16 times 2 times 0.81 squared, etc. So this will equal 16 plus, I can factor out 16 times 2, assuming that this series converges. Okay? You wouldn't be able to do that otherwise, but let's just leave it alone. Let's just rewrite it as a series, just to be safe. Okay? So I go n equals 0 to infinity. I have 16 times 2 times a, which will be 0.81, times r, which is the ratio of these two, which is 0.81 squared over 0.81, which is just 0.81. And then, yeah, this becomes basically your a value, and this will be convergent because 0.81 is less than 1. So this will equal 16 plus 32 times 0.81 times 1 all over 1 minus 0.81. Okay. And if you put that in your calculator, you get approximately 152.42 feet. Okay, thanks for watching.